Okay, so welcome back. Today, in this video, we are going to be talking about how voltage and current behave when we wire things in parallel. Now, we've already talked about series, which meant wiring things into the same branch or the same path of current. So when we talk about wiring things in parallel, what we mean is wiring them into separate paths, meaning that the current that flows through one does not flow through the other. They're in kind of isolated, separate paths. And what that's going to look like is it's kind of the same as what we're about to do right here, hooking up one single light bulb by itself in a path. Right, so we got our power supply. The voltage goes from the current goes from one side of the voltage source through the resistor and right to the other side. So what I can do now is I can take these probes, and instead of breaking the path and connecting them in series, what I can do is I can add them to the probes over here, like this. And what I want you to do is pay close attention to what happens to the brightness of this bulb when I connect this one. So really just pay attention. Is it getting any dimmer or brighter? Well, hopefully your answer here is no. When we hook this up, really it's not impacting this one at all. And we can kind of show you that by unscrewing this one a little bit and turning it back on. Off, on, off, on. In fact, let me go over here so you can just see. Right, so that's on, off, on, off. So there's no effect to this one right here. And that's one of the telltale signs for how things are wired. If they affect each other, then they're wired in series. If they don't, then they're wired in parallel. Right, so we can show you what that looks like. If we were to take this one off here, let's put them in series and test that. Let's take this here. And so now they are wired into the same path of current. And what you'll see is that when I unscrew this one, the other one turns off. Because if we break the path of current here, current without the light bulb in place, current can't jump across. If we crank this voltage up high enough, you bet it would find a way to go from one of those to the other, but that would cause a lot of sparks and potentially fire. But under low amounts of voltage, reasonable amounts, if we break the path with one, it can't continue to get through. Right? These are one path. You turn it, one light goes out, they all go out. If you've heard the 12 Pains of Christmas, then you know what that is. Right? One light goes out, they all go out. This is how Christmas lights used to be wired. They would wire one string all together like that. So when one would go out, the whole branch would. So you'd have to find which bulb was dead and replace that. It was a big pain in the butt. But instead, what we do now is we wire them in parallel. So that way, one, they don't have to share the voltage as much. But when one light does go out, the other one still stays lit. And you can easily find which bulb it is and replace it. But one thing you do need to notice here is the amount of current, right? Right now we got 6 volts and about 0.3 amps. But when I add this one in, the amount of current just about doubles. And that's very different than what we just saw in series. We saw that when we added more and more resistors in parallel, when we added more and more resistors in series, the amount of current went down because we were adding more resistors into the same path of current, so they were slowing it down. But when we wire things together in parallel, we're not stopping it. We're actually giving the electrons a whole nother path to flow through. Yeah, there's still some resistance here, but we've opened up another path, which allows more current to flow through. And if we hooked up a third one, we'd be able to see this as well. So if we connect this one into this slot here, we'll get this one a little bit closer here, this one here. So when we put this one in, well, now the current is just about tripled. Right? We had about 0.3, but when we add these other two branches in parallel, we triple it. We get to 0.9. Now you might be asking yourself, well, wait a second, Mr. T. I thought you just said that when they're wired in parallel, they don't affect each other. And you just turned off that middle one where that connected, and that affected this bulb too. So aren't those affecting each other? Well, they are and they aren't. What you can kind of see here is that in order for this side of this light bulb to get back, it's got to piggyback off of this wire here. in order to get onto here, which is why we disconnected both of those. So we didn't really, what we really mean by this is if we take out this middle one here, the other ones can still light because the wires are all still connected, right? So we've still got a complete uninterrupted path from one side of the battery to the other. So they're all in their own separate paths of current. Turning off one does not affect the other, right? Like if I unplugged this one, the other two still stay on. The only difference, and so if we unplug this one, the other two still stay on. But that's a very interesting and kind of counterintuitive thing that we're experiencing here. We're adding more resistors to a circuit, but we're getting more current. That doesn't make sense. More resistance means more current with the same amount of voltage? That doesn't work. Well, here's what's happening. Let's take a look at how much voltage each one is actually getting. So we'll turn our voltmeter back on, and we'll measure the voltage across each bulb. So we'll go across bulb number 1 here, and we're getting about 6 volts. We go to bulb number 2 here, getting about 6 volts. Go to number 3 here, and again, still about 6 volts. Now that should also be causing you some confusion. Wait a second, I thought we just established in the last video that conservation of energy is a thing. We're supplying 6 volts, and we're using 6, 6, and 6. What? How can we supply 6 volts but use 18 volts? That doesn't make sense. That's not conservation of energy. That's like free energy. I've seen lots of videos on YouTube talking about free energy. Are you telling me those are real now? Well, no. Here's the deal. What this means, that 6 volts of potential. 6 volts of potential. It means it has the potential to apply 6 volts to each branch that you hook up to this voltage source here. So you can think of that as it has the potential to push with 6 volts of energy. Well, if you think of that as like a person, well, a person can push with one arm. I can push with 6 volts. I can push with a certain amount of force. Well, I have a second arm. So I could push 2 different things. And, I don't work out or anything, but, I'm a reasonable, healthy, fit person. And so I'd say both my arms are about as strong as the other one. So I can push equally with each one. So I could push with 6 volts with this arm. I could push with 6 volts with this arm. And then I've got 2 legs too, right? So you can't see them, but they're kicking underneath here. So I could do 4. Now, this takes up a lot more energy than just this. I can do this for a lot longer than I can do this. So that's where your conservation of energy still applies. Yes, we can push each bulb with 6 volts of energy, but take a look here. Look at how many more electrons we're using. Now, this is a nice power supply, so it's kind of like an infinite supply because it's coming right from the wall. But if this was a battery, well, take a look. Now I've got 0.9, I've almost got a full amp of current leaving this power supply. And so if that was a battery, that would mean that I'd be losing almost a full coulomb of charge every second. Whereas if I've got only one hooked up, well, now that's only about 1/3 of an amp. So this would allow me to go for longer, right? I could keep this same light bulb lit for a lot longer than I can do all 3. But if I plug them in here, yeah, I can make them all still have 6 volts, but now I'm losing my electrons a lot faster. Now again, with the power supply, we've got kind of an infinite supply as long as I pay my electricity bill. But here, if this was a battery, that's only got a finite amount of electrons stored up in those chemicals. So this would cause the battery to die out a lot sooner. So it's not violating conservation of energy. It's just using up that potential faster. It's kind of think about it as your gas tank, right? Your car can drive a certain distance on the amount of gas. Now, you can drive faster, right, if you go at a faster speed, but you still got the same amount of gas to use. So you're not necessarily going to get that much farther. You're not really going to gain a whole bunch more energy by driving faster. You're just going to use it up faster. So that's kind of what's going on here. So the rules for how voltage and current work in parallel are kind of the opposite for what we just learned in series. Right? In series, we saw that the voltage was split up, but the current was the same. Well, here, the voltage across each thing is the same, and the currents are adding up. Right? Like if we unplug, I'm going to go just a little bit more just to get that to be the, yeah, there we go. So we got 0.3 amps of current through 1. Now this is an identical bulb, so it should give us an identical amount of current when we've got the same amount of voltage. Right? So 6 volts going to this, 0.3 amps. I apply 6 volts to this one. So now there's a total of 0.6 amps. So that 0.3 from this one and the 0.3 from this one added up. And then if we go here again, well, that's another third identical bulb. So 0.3, 0.3, 0.3 goes up to 0.9. The currents add up, just like the voltages added up in series. So the rules kind of flip-flop. In series, they would split the total supplied voltage and then just have the same amount of current, just because that's kind of the name, being series being the same path of current, series same current. Here it's the opposite. Parallel means you're hooking up each branch to the voltage source separately, so just same voltage, right? Because they're separate paths, same voltage. Each one gets the same voltage. And then the currents are adding up. The total supplied current here is 0.9 amps, and that's going 0.3, 0.3, 0.3. And hopefully you saw that in your lab as well. The wire resistivity made the voltage a little bit tougher to see, but that's the same pattern. They just flip-flop. In series, they share the voltage, current is the same. In parallel, they share the current, the voltage is the same. And again, those spread it up equally, right? They split it up equally. 0.9, 0.3, 0.3, 0.3. Again, it's going to be a little bit different when we have different amounts of resistance. And that's what we're going to take a look at in the next video.